I want everyone to copy this about glycerol and triglycerides. While we wait for others, what happens to triglycerides in your stomach? I want everyone to copy this. Okay, everyone copied. Please send me a chat message. Everyone copied this information. Okay, a couple of more minutes. This is the most important reaction. You guys can see one triglyceride will be broken into one glycerol and 3 fatty acids during a hydrolysis reaction that is catalyzed by the enzyme called lipase. You can use lipase or you can use acid. We learned this reaction in chapter 16. If you take ester, triacylglycerol is ester. When you add water in the presence of acid, what happens? It splits into alcohol and carboxylic acid. It's the same reaction we are just learning. And this takes place in your stomach. So acid hydrolysis takes place in your stomach. The only difference is instead of acid, it uses enzyme called lipase. Is everyone done? I'm going to show you guys acid hydrolysis and base hydrolysis. Okay. So now let's summarize the reactions of triglycerides. So the first reaction is acid hydrolysis. We just saw that. So in acid hydrolysis, what happens? If you take a triacylglycerol, and if you add water, we need 3 molecules of water because the glycerol contains 3 alcohols. You form glycerol. This is exactly what happens in your stomach. And then you form 3 fatty acids. This is acid hydrolysis. And this can take place in the presence of acid or enzyme lipase. Or enzyme lipase. So what happens in your stomach is this glycerol will dissolve in water, and these fatty acids, because they are very long chain carbons, they are not soluble in water. That's how they separate from each other. In your stomach, the glycerol will dissolve in water, but these fatty acids, because of long carbon chains, they are not soluble in water. Next, the next reaction is base hydrolysis. Base hydrolysis is also called saponification. Why we call this saponification? Because this process is used in making soaps. This process is called saponification, and we saw this in chapter 16. It's the same thing. So if you take triacylglycerol, if you take triacylglycerol and if you add a base like NaOH, I need 3 of them, 3 molecules of NaOH, 3 molecules of NaOH. Instead of using acid, this time you're using base. Again, you'll form glycerol. But you will form sodium fatty salt. You form sodium fatty salt or fatty acid salts. And this sodium fatty acid salt is your soap. I'm going to show you guys these reactions. I'm just generalizing here. Next, the third reaction is hydrogenation. Why we can do hydrogenation? What is hydrogenation? Adding what? Adding hydrogen. Adding hydrogen is called hydrogenation. So if you take unsaturated fat with double bonds, it has to be unsaturated. You can do hydrogenation only on unsaturated fats. If you take unsaturated fat with a double bond, and if you add hydrogen, if you add hydrogen, it will convert into saturated fat. It will convert to saturated fat. So unsaturated fat becomes saturated. So this is how they convert liquid vegetable oil. This is exactly how they convert liquid vegetable oil into margarine or stick margarines and so on. So you guys can see, you can convert. Application is vegetable oil. Vegetable oil is unsaturated fat. Vegetable oil is converted to what? Is converted to, depending on hydrogenation, you can convert them to soft margarines or stick So if I have to summarize here, what I can say, animal sources such as butter and lard contains what? Lot of saturated fat. Lot of saturated fat. So whenever you're consuming products from animal sources, try to limit the consumption. Try to limit the consumption. So these are the three reactions that you guys has to remember for triacyl glycerols: acid hydrolysis, base hydrolysis. Base hydrolysis is also called saponification, and hydrogenation. We can do hydrogenation only on unsaturated fatty acids to convert them into saturated fat. Is everyone done copying? Please let me know. Now let's look at some reactions. You guys can see here vegetable oils in the liquid form or on hydrogenation converted to soft margarine or stick margarines, which are solids. Now let's look at the reaction. Anyone, please solve this. What is the answer for this? Yes, the answer is B. You guys can see you're doing hydrogenation. On hydrogenation, triglyceryl trioleate becomes glyceryl tristearate. How do we know stearate? Because stearate is a saturated fat. That's how I know. Because this is hydrogenation process. Triolate is triacylglycerol, converts this to what? Saturated fat, which is glyceryl tristearate. We know stearate is saturated fat. So the answer is stearate. Now, please look at the reaction. Here we are looking at unsaturated fatty acid. This is cis. Why this is cis? Why this is cis? Because both bonds are facing down. If the bonds are on opposite sides, it becomes trans. Everyone has to know how to identify cis and trans double bonds. So you guys can see when we are doing hydrogenation, a small number of cis double bonds are converted to stable trans double bonds, causing in the chain of overall structure of fatty acids. You have to be aware of that. So what happens is sometimes, just to give you guys an example, when you buy olive oil, yes, a freshly prepared olive oil from olives contains fatty acids with cis double bond. Now, as the time goes on, when it has a longer shelf life, when it stayed on the shelf for a longer time, what happens is it was exposed to sun. It was exposed to sun. Those molecules are exposed to sun. Um, what happens is these molecules absorbs energy, and those cis bonds are slowly changing into what? Trans double bond. And trans double bond is more stable. It almost behaves like a saturated fat. That's the reason why when you go to HEB or any other stores, the olive oil that is almost going to expire will be on sale. Will be on sale for $4, $3, because they know most of the cis double bonds in fatty acid are converted to what? Trans double bond. So even though it is in the oil form, but it's almost acting as a saturated fat. So a lot of people think, oh, olive oil is on sale, I'm going to buy a lot of bottles. But what they don't understand is they're not buying olive oil, they're actually buying saturated fat, because cis double bonds are slowly converted to trans double bonds on shelf in olive oils. So you'll be aware of that. That's the reason why olive oil comes in tinted glass. You guys can see the glass package that they have. It's a tinted glass. It's not normal white glass. If you see olive oil in a normal glass without any tint, don't even buy it. It doesn't have any shelf life. So here you guys can see I have a cis. You guys can see how on hydrogenation, some of the cis double bond is changing into trans, which is our undesired side product. And this is our desired saturated fat. The double bond becomes a single bond. The double bond becomes a single bond. Next, try to solve this. Try to solve this. The answer is going to be what? The double bond disappears. The double bond becomes what? Single bond, and add hydrogens. That's it. Please do this. I'll show you guys the answer in a minute. You're doing hydrogenation on triacylglycerol. You're doing hydrogenation on triacylglycerol. So let me show you guys the product. Are you guys done? Can I show you the product? So that's the product. Everyone see the double bond disappeared and you have all single bonds. In hydrogenation, all it happens is the double bond becomes single bond and you're adding hydrogens. That's it. You're adding hydrogens on the double bonded carbons. Okay, let's move on. Let's look at this acid hydrolysis. Look at this acid hydrolysis. This is triacylglycerol. These are ester bonds. Everyone see that? These are ester bonds. This is glycerol. This part of the molecule is glycerol. This part of the molecules are acids. And you guys can see when you add water in the presence of acid or lipase, what happens? The ester bond breaks. The ester bond breaks between oxygen and carbonyl to form glycerol and corresponding fatty acids. This is exactly what happens in your stomach. This is acid hydrolysis. Please copy this. This is acid hydrolysis. Once you are done, please send me a group chat message so that I know you guys are done and I can move on to the next slide. You're just adding water to break the ester bond to split the ester into corresponding alcohol and acid molecules. Even if you look at the name, you guys can see glyceryl tripalmitate. This is the triacylglycerol, glyceryl tripalmitate glyceryl becomes glycerol, tripalmitate becomes three palmitic acids. Tri means three, we have three of them. Palmitate, ester becomes acetic acid, palmitic acid. Okay, next. Now let's look at base hydrolysis. That's the base hydrolysis. Now I'm going to take the same ester, glyceryl tripalmitate, and I'm adding a base. Sodium, NaOH is sodium hydroxide, which is a base. In the presence of strong base, what happens? You still form glycerol. But this time you're not forming fatty acids, but you're forming sodium salts of fatty acids. Do you see here, instead of hydrogen, what do you have? Na plus O minus, Na plus O minus, Na plus O minus. These are three sodium palmitate. This is a soap. And this process is called saponification. And this process is called saponification. Is everyone done? A couple of minutes. If you guys copy this into your class notes, copying always give you guys a practice. Writing it down makes you memorize much better than just looking at. Okay, now let's solve this problem. Let's solve this problem. We solve this. First of all, when you look at this equation, now you guys are thinking, is this equation is acid hydrolysis or base hydrolysis? Please send me answers. Is it acid hydrolysis or base hydrolysis? Just by looking at this. So I know we have triacylglyceride. We have triacylglyceride. This is ester. I see ester bond. So this is triacylglyceride. I can clearly see glycerol. And I'm looking at water and lipase. Is it acid hydrolysis or base hydrolysis? Please send me chat messages. Please send me chat messages. Look at this. I'm looking at water and I'm looking at lipase. Very few people are sending me the answers. Is this a acid hydrolysis or base hydrolysis? It is an acid hydrolysis. Yes. Why it's acid hydrolysis? Because I'm looking at enzyme. In your stomach, what do you have? Either you have enzymes or you have acid in your stomach. So if it's undergoing acid hydrolysis, what do you form? You form glycerol. You break the bond here between oxygen and carbonyl, and then you're adding water. Hydrogen goes here, OH goes to carbonyl. So you form corresponding glycerol and 3 fatty acids. So please draw the structures, and before I show you guys the answer, please draw the structures. Okay, let's look at the answer. So you guys can see the triacylglycerol is converting into glycerol and corresponding fatty acids. This is the structure for glycerol. You cannot forget this. There is a small mistake here. This is not CH2, this is CH. It's supposed to be CH, not CH2. This middle carbon supposed to be only CH. Why? Carbon can form only 4 bonds. Here it's showing 5 bonds. It's supposed to be only CH, not CH2. Now let's solve some problems from your textbook. Page number 601. Page number 601. 17.29, 17.33, 17.35, and 17.37. I'm just sending you guys a chat message. Page number 601. Yes, I think there is also a mistake here. These oxygen supposed to be double bonded on carbonyl. They're missing the carbonyl. This supposed to be double bonded, and this supposed to be double bonded. To be a carboxylic acid, this carbonyl to be double bonded and this carbonyl to be double bonded. So there are some mistakes on this slide. This carbon supposed to be CH, not CH2. This supposed to be CH. And this supposed to be carbonyl, C double bond O, C double bond O. Now please go to page number 601. Let's move on to the next topic. The next topic is phospholipids. Now, before we get into phospholipids, I just want to show you guys the difference between triacylglycerol and glycerophospholipid and sphingomyelin. So these are the differences. So you guys can see I'm showing the same thing here. So this is glycerol. And this is also glycerol. We know how glycerol looks like. But that's not glycerol. So I'm drawing the structures for all of them to show you guys how it looks. So if you attach 3 fatty acids to a glycerol, if you attach 3 fatty acids to a glycerol, What type of bond is this? This bond is ester bond. So these bonds are ester bonds. So you have a glycerol and you're attaching 3 fatty acids to a glycerol by using an ester bond, then it becomes what? Triacyl glycerol. So this is triacyl glycerol. Now please look at here. You have a glycerol and you're attaching not this time 3 fatty acids, but only 2 fatty acids. You're attaching only 2 fatty acids. And these fatty acids are attached by using what bond? Ester bond, just like before. Just like in triacyl glycerol, these are ester bonds. This is also ester bond. But this time, you're not attaching, the third one is not attached to fatty acid, but this attached to PO4. PO4 is called phosphate group. It's attached to PO4, and this PO4 is attached to amino alcohol. Amino alcohol. So please look at here, the difference between triacyl glycerol and phospho or glycerophospholipid. Why this is called phospholipid? Because this contains phosphate group. That's the reason why this is phospho. It contains glycerol, so it's glycero. And this is a lipid, so it's a glycerophospholipid. Everyone say the differences. If you have a glycerol attached to 3 fatty acids, it's called triacyl glycerol. If you have a glycerol attached to only how many fatty acids? 2 fatty acids. And the last fatty acid in glycerol is replaced with what? Phosphate group, and phosphate group is attached to amino alcohol. Then this becomes glycerophospholipid. But in glycerophospholipids, we can have 3 types of amino alcohols. We have different types of amino alcohols. The most common ones are that we use here are choline. I'm going to show you guys the structures. We have 3 different types of amino alcohols that we use on glycerophospholipid. Serine, and ethanolamine. So glycerophospholipids are well known for cell membranes. Our cellular membranes are made of glycerophospholipids. Everyone knows that. And we also know glycerophospholipids contains polar and non-polar region, which allows them to interact with both polar and non-polar substances. Don't you guys remember? You guys heard from anatomy and physiology. Phospholipids contains polar head and non-polar tail. Don't you guys remember? So this is polar head. If you guys remember, this part of the molecule is polar. This is your polar head in glycerophospholipids. The rest of the molecule is non-polar. So that's the reason why they say it contains polar head and non-polar tail. Non-polar tail. Well, the well-known glycerophospholipids, I'm just talking about glycerophospholipids, are lecithin. I don't know if you guys heard about these. Lecithins and cephalins. These two are well-known glycerophospholipids. They both differ in what? Amino alcohol. I'm going to show you guys the structure. Lecithin contains choline as amino alcohol, and cephalin contains ethanol amine as amino alcohol. That's the difference. That's the difference. Lecithin contains choline as amino alcohol. Cephalins contains ethanol amine as amino alcohol. That's the difference between these two. And these are the two types of glycerophospholipids. That are abundant in what? Anyone remember? Where we find these two? We can find them in brain and nerve tissue, as well as egg yolk, wheat germ, and yeast. So once again, look at the difference between triacylglycerol and glycerophospholipid. In triacylglycerol, we have a glycerol attached to what? 3 fatty acids by using a ester bond. But in the case of glycerophospholipid, we have a glycerol attached to only 2 fatty acids by using ester bond. And the third one is attached to phosphate group. That's the reason why it's called phospholipid. Phosphate group, and this phosphate group is attached to amino alcohol. And this part of the molecule, phosphate group, where the phosphate group is called polar head, and the remaining part of the molecule is called non-polar tail. The remaining part of the molecule is called non-polar tail. So that's the reason why they are used on cell membranes, so that these membranes can interact with both polar and non-polar substances. So polar head is strongly attracted to water, and non-polar tail is hydrophobic. It doesn't like water. Everyone see the difference. So one molecule contains polar and non-polar. And the well-known examples for glycerophospholipid is lecithin and cephalins. Lecithin contains choline as amino alcohol. Cephalin contains ethanol amine as amino alcohol in the structure. That's how they differ from each other. And they both are abundant in brain and nerve tissue. as well as in egg yolk, wheat germ, and yeast. Let me write down here G for glycerol, Fa is for fatty acid, and S for sphingosine. I'm going to show you guys right now. I'm going to show you guys the sphingomyelins. This is sphingomyelins. Any questions on triacylglycerol and glycerophospholipids before I show you guys the structures? Any questions on the differences between triacylglycerol and glycerophospholipids? Please send me messages. Yes, cephalines contains ethanol amine as amino alcohol. Yes. Lecithin contains choline as an amino alcohol here. That's the difference. Lecithin contains choline as amino alcohol. Cephalines contains ethanol amine as amino alcohol here. Now, we are going to look at sphingomyelins. Sphingomyelins contains sphingosine. Please look at here. S stands for sphingosine, not glycerol anymore. This is not glycerol. This is sphingosine. Sphingomyelin contains sphingosine. I'm going to show you guys the structure. And this sphingosine is attached to only one fatty acid. Is attached to only one fatty acid, and this bond is not ester bond. This bond in sphingosine is amide bond. That's the difference. Please be aware of this. This is not ester anymore. This is amide. I'm going to show you guys the structure. This is not an ester bond. This is amide bond between fatty acid and sphingosine. Between fatty acid and sphingosine. So this is an amide bond between sphingosine and fatty acid. And then we have only one fatty acid. Please be aware of that. And then this sphingosine is also connected to phosphate group, just like glycerophospholipid. phosphate group, and this phosphate group is attached to amino alcohol. Amino alcohol. This sphingosine is attached to amino alcohol. So these sphingomyelins, I would like to talk about sphingomyelins, where we can significance of these. If you're done drawing the structures, I would like to talk a little bit about significance of sphingomyelin. Everyone see the differences between tri-acylglycerol, glycerophospholipid, and sphingomyelin. In sphingomyelin, you have sphingosine. S stands for sphingosine, and sphingosine is attached to fatty acid by using an amide bond. In other two compounds, those are ester bonds, but here it's a amide bond. And sphingosine is connected to phosphate group, and this phosphate group is connected to amino alcohol. And we have three types of amino alcohols. We just talked about choline, serine, and ethanol amine. If everyone is done, I would like to talk about the significance of sphingomyelin. Please send me a chat message if you're done. Only two bonds in sphingomyelins. One bond to fatty acids, another bond to phosphate group and amino alcohol group. That's it. Okay, now let's talk about the significance of sphingomyelins. Sphingomyelins are abundant in the white matter of the myelin sheath. I don't know. This is a myelin sheath, a coating. This is like a coating surrounding the nerve cells. That increases the speed of nerve impulses. So that's the role. The sphingomyelin, they are found around this white matter. They are found around the white matter of the myelin sheath. This is a coating around the nerve cells, and that coating, that white myelin sheath, increases the speed, nerve impulses, and insulates and protects the nerve cells. So what happens if this myelin sheath loses the sphingomyelin? When the myelin sheath loses sphingomyelin, you guys can see what happens when that white myelin sheath loses the sphingomyelin. It deteriorates, and the transmission of nerve signals is disturbed, especially in multiple sclerosis. Sphingomycin is lost from the myelin sheath. It's very hard for me to spell these names. So this is the reason why people get multiple sclerosis. Sphingomyelin is lost from the myelin sheath. So when it's lost from the myelin sheath, what happens? It deteriorates, and the transmission of the nerve signals is impaired. This is exactly what happens in multiple sclerosis. The symptoms include, what type of symptoms that you can observe? So you guys can see the sphingomyelin found in eggs contains sphingosine, and the fatty acid is palmitic acid, phosphate, and amino alcohol is choline. Well, if you guys think about a premature infant with a respiratory distress, so usually they have having hard time breathing because their airways are blocked and the lungs are not completely developed. So one way to measure the maturity of lungs of a fetus is to measure the lecithin to sphingomyelin ratio. You guys may do this at hospitals. It's called LS ratio. So let me move this a little bit higher. LS ratio. If the LS ratio is 2.5, if LS ratio is 2.5, that indicates mature fetal lung function. If LS ratio is less than 1.5, is less than 1.5, it indicates high risk of a high risk of IRDS. IRDS stands for infant respiratory distress syndrome. That we write down here. So what happens if the LS ratio is too low? What they do is they prescribe them steroids to the mother. So next topic is going to be steroids after this. So you guys can see the significance of sphingomyelin. Please write down. If everyone done copying this, please let me know so that we can go back and look at the structures. Little up. Okay, let me move this up. Can you see everything, ma'am, now? Okay, are you guys done copying all this? Please let me know through chat message. Okay, now let's look at one more time the differences between triacylglycerol, glycerophospholipid, and sphingomyelin. In triacylglycerol, we have a glycerol attached to 3 fatty acids with the ester bond. In glycerophospholipid, you have 2 fatty acids attached to a glycerol by using ester bond, and the third one is phosphate group attached to amino alcohol. And this part of the molecule is called polar part of the molecule, and the rest of the molecule is non-polar in nature. And we have three different types of amino alcohols. We have choline, serine, and ethanolamine. I'm going to show you guys the structures. The famous examples are lecithin and cephalines. In lecithin, we have choline as amino alcohol. In cephalines, we have ethanolamine as amino alcohol. And these are the two glycerophospholipids that are abundant in brain and nerve tissues, as well as egg yolk. In sphingomycin, we have sphingosine attached to fatty acid by using an amide bond. And the second one is attached to phosphate group, and the phosphate group is attached to amino alcohol. This is the whole summary. Now I'm going to show you guys the structures. Okay, now look at glycerophospholipid. You have a glycerol attached to two fatty acids, and then the third one is attached to phosphate, and a phosphate is attached to amino alcohol. And we have three different types of amino alcohols. I told you guys, please write down the structures for choline. This is choline, this is serine, and this is ethanolamine. We have three different types of amino alcohols. Please draw the structures. These are the three different types of amino alcohols. We have choline, so this is the way you remember. If nitrogen is surrounded with three CH3s, that's choline. If you have carbonyl with nitrogen, it's serine. If you have just NH3 attached to CH2, it's ethanolamine. So you have choline, serine, and ethanolamine. Please draw the structures for all these three in your class notes. Please, everyone copy the structures of choline, serine, and ethanolamine. If you're done, please send me a message. If you're done, please send me a message. Okay, now let's look at choline, lecithin, and cephalene. Now please look at the structure. You guys can see this is glycerol. These two are fatty acids. And this is a phosphate group. and you guys can see this amino alcohol is choline. This part of the molecule is called polar. Remaining part of the molecule is non-polar. And this is the structure for cephalene. Again, everything is same. You have glycerol and you have two fatty acids. And you guys can see phosphate group. And this time you have ethanol amine. Ethanol amine. So please copy the structures for lecithin and cephalene. Please copy the structures of lecithin and cephalene. The amino alcohol part of the molecule is polar head. The rest of the molecule is non-polar in nature, especially the fatty acids chains. Please copy the structures of lecithin and cephalene. If you're done, please send me the message. If you're done copying the structures, please send me the message. Is everyone done? Is everyone done? Okay, now let's look at the how you guys learned a simple way to draw the glycerophospholipids. You see the polar head like this, and you guys must have seen non-polar tails. So the way they have drawn in chemistry is this: polar head is amino alcohol part and phosphate part. This is polar head. This is glycerol here, and the rest of the molecule fatty acids are non-polar tails. Everyone see that? So in biology books, this is a simple way for them to show you guys the polar head and non-polar tail. From the chemistry point of view, you're actually seeing the molecules. Which part of the molecule is polar and which part of the molecule is non-polar. So if someone asks you guys, what are the components of glycerophospholipid? You guys can see amino alcohol. In this case, this is choline. Phosphate group is phosphoric acid, glycerol, and fatty acids. All these are the components of phospholipid. You guys can see amino alcohol, phosphate group, which is phosphoric acid, glycerol, fatty acids. So you have four components that are made in glycerophospholipid. You have choline, amino alcohol, phosphoric acid, glycerol, and fatty acids. By looking at the colors, by comparing the colors, we can see which one is polar and which one is non-polar. Now I'm going to show you guys the structure of sphingomyelins. Can I move on to sphingomyelins? Can I move on to sphingomyelins? Only two people are responding. I want everyone to respond in chat message. Okay, now let's look at sphingomycin. This is sphingosine. Please look at here. Everything that was shown in yellow color, the structure of the molecule that is highlighted in yellow color is sphingomycin or sphingosine. The part of the yellow color, the structure that was highlighted in yellow color is sphingosine. Please draw the structure, and then you have a fatty acid attached to nitrogen in sphingosine. Everyone see that? That's the reason why this is amide bond. And then you have phosphate group and amino alcohol group. So please draw the structure for sphingomyelin. Sphingomyelin contains sphingosine. Everyone see the structure in yellow color. The structure that was highlighted in yellow. It's almost like I'm a colorblind. Is it brown? It's almost like a dark brown. We are going to look at steroids. So we are going to look at steroids. Steroids are lipids. So steroids are lipids that do not contain fatty acids. Steroids are lipids that do not contain fatty acids. Lipids that do not contain fatty acids are called steroids. So how do we identify steroids? We identify steroids by using steroid nucleus. I'm going to show you guys the structure. We identify steroids by using steroid nucleus. So this is the nucleus. Cyclohexane ring attached to cyclopentane ring attached to cyclohexane So this is called steroid nucleus, and we use A for the steroid. This is B cyclonucleus. This is C, and this is D. So these four rings are designated as A, B, C, D. A, B, C, D. These four rings are, in these four rings, what do we have? If you observe clearly, you guys can see in steroid nucleus, we have, if you guys observe, what do you see? You have 3 cyclohexane rings. We have 3 cyclohexane rings and 1 cyclopentane ring fused together. That's exactly what we did. So you guys can clearly see there is no fatty acid in steroids. So lipids that do not contain fatty acids are called steroids. And we identify steroids by using steroid nucleus. And we have 3 cyclohexane rings and 1 cyclopentane rings. And clearly you guys can see we are designating these rings by using A, B, C, D. D is for cyclopentane ring. And we also start numbering these rings. So if you're looking at the carbons, we have a lot of carbons. The way we start numbering is from A. So please look at the numbering here for the ring system. For the ring system, this is 1. We start numbering from here for steroids. 2, 3, 4, and this carbon is 5. Please look at here. This is exactly how you number these. 6, 7, that's 8, that's 9, that's 10, and this is going to be 11, 12. This carbon here is 13. This is 14. This is 15. This is 16. This is 17. This carbon here is 18. And this carbon here is 19. So this is the way we number these rings. We start from A, and then we go all the way to D, and then come back and name these methyl groups. So you guys can see the numbering system. Now the famous example for steroids is cholesterol. The famous example for steroid is cholesterol. Now, please look at the structure for cholesterol. I'm going to draw the structure for cholesterol. I'm going to have this ring. This is A. This is B. No, I'm missing something here. This is B. This is C. This is D. Now look at the differences. This is a core ring. And you guys can see there's a methyl group here. There is a methyl group. So this is our steroid nucleus. But to make it to cholesterol, please look at here. I'm going to place a double bond between 5 and 6. And on carbon 3, you have OH hydroxyl group. You have hydroxyl group, and then you have a long chain carbons on carbon number 17. I'm sorry. So this is cholesterol. Clearly, you guys can see cholesterol contains steroid nucleus. Clearly, you guys can see cholesterol contains steroid nucleus. So I want everyone to copy the structure of cholesterol and steroid nucleus. Now we are going to talk about the significance of cholesterol. Now we are going to talk about the significance of cholesterol. If you're done drawing structures, please let me know. We can move on. So in this class, we are going to look at, under this steroids, we are going to look at cholesterol. We are going to look at bile salts, the structures of bile salts, lipoproteins, and we are going to look at the structures, some steroid hormones. This is the last topic for this chapter. We are going to talk about cholesterol, bile salts, lipoproteins, and steroid hormones. Is everyone done copying the structures of cholesterol? Okay, let's talk about cholesterol. So cholesterol is a main component of cellular membranes. The myelin sheath, brain, and nerve tissue. So you guys can see it's everywhere. It is also found in liver and bile salts. We're going to look at the structures of bile salts. When we talk about bile salts, you guys heard about gallstones. Gallstones are formed in the gallbladder. Yes. And we are going to look at how these bile salts becomes gallstones. So we're going to look at that. But for now, you guys can see they are also found in liver and bile salts. And large quantities of these are found in the skin. And the main advantage is some of it will convert vitamin D when your skin is exposed to sunlight. So this is one of the reasons why people always say you need at least 1 hour of sun every day. If you are exposed to at least 1 hour of sun, especially in the evenings from 4 to 7, especially in the evenings from 4 or 5 to 7, at least 1 hour, if you can be exposed directly to the sunlight, large quantities of cholesterol in your skin will become vitamin D. In vitamin D. In adrenal gland, cholesterol is used to make steroid hormones. Like testosterone. I'm going to show you guys the structures. Testosterone. How do you spell this? Steron. Testosterone, estrogen, the liver synthesizes cholesterol from carbohydrates, from fats, and proteins. So you guys can see even your liver makes cholesterol, whatever it needs for the body, from fats, carbs, and proteins. And if you want additional cholesterol is coming from where? From meat, milk, eggs in the diet. But you have to be aware, there is no cholesterol in vegetables and plant products, any plant product that you can think of. Now let's discuss about cholesterol, because it can cause heart attacks. We all know that. A cholesterol level less than 200 milligrams per deciliter is desirable in adults. So if you can have less than 300 milligrams, it's desirable. In adults, if the cholesterol is greater than 300 milligrams, causes a condition called familial hypercholesterolemia. Familial hyperlemia. I'm going to call this FH. FH is caused by genetic mutation that blocks the removal of cholesterol from the blood, resulting in the formation of deposits on the arterial walls. We call that plaque. So American Heart Association recommends we consume no more than 300 milligrams per day. So they say don't take more than 300 milligrams of cholesterol per day. So 300 milligrams. If you eat one large egg a day, you're going to get 200 milligrams of cholesterol, one large egg. If you eat 3 ounces of beef, you get 370. So 3 ounces means very small piece, but a lot of people eat French fries and they eat a lot of couple of hamburgers and so on. So they're going to get a heart attack very fast. So if you consume one large egg, you're going to get 200 milligrams of cholesterol. If you eat one fried chicken, let's say one small leg piece, you're going to get 130 milligrams of cholesterol. If you eat chicken with no skin, 3 ounces, you're going to get almost 80 milligrams of cholesterol. Fish, salmon, especially salmon, 3 ounces, you're going to get 40 milligrams of cholesterol. If you drink 1 cup of whole milk, you're going to get around 35 milligrams of cholesterol. So you guys can see American Heart Association recommends less than 300 milligrams of cholesterol per day. 300 milligrams of cholesterol per day. So all you have to do is eat 1 egg, and then everything else for a day is plant-based food. Eat everything vegetables. You will live a long, healthy life. Or 1 3 ounces small piece hamburger, and rest of it is all plant-based, vegetables, salads, greens, fruits. So saturated fats and cholesterol So this is the significance of cholesterol. Next, bile salts. If you're done copying, please let me know. We can move on to the next topic, which is bile salts. Is everyone done copying? Yes. Now let me show you guys the structure of bile salts. So let's draw the structure for bile salts, and then we will discuss about bile salts. Bile salts are also contains steroid nucleus. You guys can see the challenges of drawing with this. So you guys can see this is O minus Na plus. This is the polar part of the region. This is the polar part, polar. If you see cholesterol, in cholesterol, we don't have any polar part. But in bile salts, we have this chain which is polar in nature. That's the main important concept. That's the main difference between cholesterol and bile salt. Cholesterol is completely non-polar, but bile salts contains polar part and non-polar part, or polar region and non-polar region. So they almost act like a soap. And we are going to talk about the significance of bile salts. So the bile salts in the body are produced they are synthesized from cholesterol in the liver and stored in the gallbladder. And stored in the gallbladder. When the cholesterol levels are higher, what happens? You form gallstones in the gallbladder. If they are too large, they may obstruct the bile duct, and that causes pain and inflammation. Now you guys can see how people get jaundice. So this is the significance of bile salts, and I am showing you guys the structure. The main difference between bile salts and cholesterol is completely non-polar, but bile salts contains polar region and non-polar region. I'm showing you guys on the screen. And because of these polar and non-polar regions, these molecules almost acts like a soap, breaking down large fat globules into smaller droplets. When the cholesterol levels are higher, you are going to form gallstones in the gallbladder. And when that happens, you guys can see it may cause jaundice. American Heart Association recommends less than 300 milligrams of cholesterol a day. One large egg, please remember this, one large egg gives you 200 milligrams of cholesterol. If you're done copying, please send me a message. If you're done, we are going to move on to next topic, lipoproteins. Are you guys done copying? Can I move on to the next topic, lipoproteins? Yes, can we move on to the next topic? Yes, please send me messages. Okay, the next topic is lipoproteins. So in the body, the lipids must be moved through the bloodstream through the bloodstream to tissues where they are stored, used for energy, or used to make hormones. But the problem is most of the lipids are what? Non-polar. And they are insoluble in polar environment of the blood. You guys can see the problem here. So the transportation of lipids is a problem here because they must be transported through the bloodstream, through the tissues. But the problem is the environment of the blood is polar and lipids are non-polar. So what happens is they are made soluble by combining them with water soluble, or you can call it polar, combining them with polar complexes called lipoproteins. So these lipids are combined with polar complexes called lipoproteins to transport them to the tissues through the bloodstream. So what is this water soluble complex? It's a combination of phospholipids plus proteins. So when you combine phospholipids with proteins, you form lipoprotein. So the shape of these ones are spherical. The shape of these lipoproteins is spherical. So a spherical lipoprotein particle surrounds non-polar lipids with polar lipids and protein to transport to body cells. There are a lot of different types of lipoproteins. Which differ in density. The well-known lipoproteins are LDLs. I think you guys heard about these before. LDL. LDL stands for what? Low density lipoprotein. And you guys heard about HDL, high density lipoprotein. You guys heard about these. And these two are used to transport cholesterol. So LDL and HDL transport cholesterol. Cholesterol is non-polar in nature. So the LDL carries cholesterol to the tissues where it can be used for the synthesis of cell membranes and steroid hormones. So LDL carries cholesterol to the tissues where it can be used for the synthesis of cell membranes and steroid hormones. When LDL exceeds the amount of cholesterol needed, by the tissues, the LDL deposits, cholesterol in arteries. That's exactly what it does. We call that plaque. Which will restrict the blood flow you guys can see what LDL does. If LDL takes too much cholesterol and that cholesterol that was not needed by the tissues, then what LDL does is it just deposits this cholesterol in arteries, creating plaque. This is the reason why we call LDL bad cholesterol. But what HDL does is, HDL picks up cholesterol from tissues and carries it to the liver, where it is converted to bile salts, which can be eliminated from the body. This is the reason why HDL is called good cholesterol. So you guys have to remember, high and low density lipoproteins transport cholesterol between tissues and the liver. So this is the significance of lipoproteins. And I'm going to show you guys the structures. The last topic is steroid hormones. I just want to give you guys the significance of steroid hormones, and then I will show you guys the structures. Are you guys done copying this? Please send me a message. You guys can see how chemistry plays an important role to understand anatomy and physiology. At the core of everything, chemistry plays a crucial role. That's the reason why all of you need to learn chemistry. Is everyone done? Can I move on to the next last topic? Steroid hormones. Hello, Is everyone done? So now I'm going to talk about steroid hormones. Steroid hormone structures are closely related to in structure to cholesterol. And they depend on cholesterol for their synthesis. And they depend on cholesterol for their synthesis. So what are hormones? What exactly they do in human body? Well, hormones are almost chemical messengers. That serve as a communication system from one part of the body to another. Examples: sex hormones, So this is the significance of steroid hormones. Please write down, and I'm going to show you guys the structures, and we will be done with this chapter. If you're done copying, please let me know so that I can show you guys the structures. Are you guys done copying this? Please send me a chat message if you need more time. Is everyone done? Please send me a chat message. Is everyone done? Okay, now let's look at the structures. So now please look at here. This is how high density, you guys can see excess cholesterol forming a plaque that can block an artery. So you guys can see A is normal artery with no buildup of plaque, and B is a artery that is completely clogged by plaque. That's the difference between normal one and a artery which is being blocked. You guys can see all this excess cholesterol by LDL is thrown here. So this is the structure of cholesterol. This is steroid nucleus, and this is the steroid numbering system. We already saw that. So this is the structure of cholesterol with OH on carbon 3. And this, if you're looking at the structure, cholesterol is completely non-polar. Completely non-polar. Now look at the answer this. Match the following components of a cholesterol. carbon chain is D. This is carbon chain is D. Steroid nucleus. Steroid nucleus is C. Hydroxyl group is A. Methyl group is B. You must be able to identify by looking at the structure. Let's look at the gallstones. This is the gallstones formed in gallbladder when the cholesterol levels are very high. Please look at how it looks. You guys can see the structures of the pictures of gallstones formed in the gallbladder when the cholesterol levels are really high. And this is the structure for bile salts. You guys can see cholesterol, which is a non-polar region. This is a polar region. And this structure helps to break the fat molecules into smaller droplets. Now, lipoproteins, you guys can see lipoprotein is a cholesterol ester. It's a lipoprotein. Now you guys can see lot of lipoproteins. Please look at here, lots of lipoproteins, non-polar lipids, being carried by polar lipoproteins. Now, this is LDL and HDL lipoprotein levels. Now let's look at the structures of steroid hormones. This is testosterone. You guys can clearly see the core structure is cholesterol, cholesterol, cholesterol. This is estrogen produced in ovaries. This is progesterone, and this is a synthetic steroid hormone. You guys can see the structures. They all contains cholesterol core structure. Cholesterol store structure. But if you guys looking at the difference between testosterone and estrogen, the difference is only in ring 1. In ring 1, we have double bond and a ketone functional group. In estrogen, we have a benzene ring with OH, which is phenol. So if the first ring is phenol, this estrogen. If the first ring is cyclohexene ring with a ketone functional group, it's testosterone. So with this, we are done with chapter 17. With this, we are done with chapter 17. All these structures are available in your textbook. If you guys, I already took the attendance. If you have any questions, please stay here. If you don't have any questions, that's it for today.